All right, so you asked about the Euclidean algorithm. So the Euclidean algorithm is used to compute the greatest common divisor of two integers, let's say a and b. And the process is just division. You take a, it's supposed to be that a be equal to a0 and b be equal to a1. So we're going to write a divided by b, you get b times some quotient plus the remainder, where the remainder is between 0 and b minus 1. Or if I want to use this notation, a0 is a1 times some remainder, I'll call it q1, plus the quotient, plus the remainder, which I'll call a2. So a2 is less than a1 and greater than or equal to 0. Now, if a2 is 0, then a0 is a1 q1, and the greatest common divisor of a0 and a1 is a1, because a1 divides a0. If a2 is not 0, if it's bigger than 0, then you take a1 and divide it again by a2. You get a quotient q2 and a remainder a3. You say a3 is less than a2 and greater than or equal to 0. And then you look at this equation. If your remainder is 0, then a2 divides a1. And if a2 divides a1, it divides a1 q1 plus a2, it divides a0. So it divides a0. And anything that divides a0 and a1 also divides a2. So a2 would be the greatest common divisor. And the Euclidean algorithm, which goes back to Euclid about 2,500 years ago, just says continue to do these long divisions. Your remainders get smaller and smaller. Eventually, they have to hit 0. And when you hit 0, the last positive remainder is the greatest common divisor. So if I take two numbers like, I don't know, 51 and 24, and I want to find the greatest common divisor. So you take, well, maybe that's too easy. I'll take 51 and 21. So you take 51 and 21, you divide 51 by 21, you get a quotient of 2, that's 42, and a remainder of 9. It's not 0. Then you take 21, you divide it by 9, you get a quotient of 2, and a remainder of 3. Then you take 9, divide it by 3, you get a quotient of 3 and a remainder of 0. So the last positive remainder, which was 3, is the greatest common divisor of 21 and 51. And if you divide 21 by 3, this goes in 17 times. You divide 51 by 51 by 3, you get a quotient of 17. Divide 21 by 3, you get a quotient of 7. And you can see the greatest common divisor of those two numbers is 3. So that's the Euclidean algorithm.
Now, how do you go backwards?
Well, okay. So here's 3. That's the greatest common divisor. It's equal to 21 minus 9 times 2, right? Okay? 3 is 21 minus 9 times 2. And then you have 9. 9 is 51 minus 21 times 2. So plug this in here. You get 21 minus 51 minus 21 times 2 times 2. That's 21 minus 51 times 2. minus times minus is plus. 21 times 2 times 2, that's 21 times 4. 21 plus 21 times 4 is 21 times 5 minus 51 times 2. So you can say that 3 is 21x plus 51y, where x is equal to 5 and y is equal to minus 2. That's what this says. So that's just working backwards, plugging in the numbers.
Thank you, Professor.
Sure.
Professor, can you go over number 23, the centralizer of A?
23 on,
The centralizer of A.
okay. Just a second. Okay. So this is number 23. We have a group G and an element A in G, and what is called the centralizer, C sub G of A. It's all elements in the group that commute with A. So all elements X such that X times A is A times X. And, sorry, call this Z, C of G. And we want to prove Z of G is a normal subgroup. So first of all, we need to prove this is a subgroup. So suppose X and Y are in this set. That means that XA equals AX and YA equals AY. So if you look at XY times A, that's X times YA, that's just associativity. YA is the same as AY. This is the same as XA times Y, again by associativity. XA equals AX, so this is AX times Y, which is A times XY. So XY commutes with A, so XY is in the centralizer. So the centralizer is closed under multiplication. Also, E times A and A times E are equal because they're both equal to A. So E is in the centralizer. So the centralizer contains the identity. So we have to show it contains the inverse of an element. So we have, if X is in the centralizer, then AX equals XA. So if you take this element and you multiply on the right by A inverse, you get that. Still equal. If you multiply on the left by A inverse, you get this. But A inverse A is the identity. So this is XA inverse. Oops, sorry, I did this backwards. No, let me do it again. So if X is in the centralizer, AX equals XA. If you multiply on the left by X inverse, you get this. X inverse AX is X inverse XA, which is just A. Multiply on the right by X inverse, you get this. But X inverse again is the identity. So X inverse A is A X inverse, which means X inverse is in the centralizer. So the centralizer contains the identity, it's closed under multiplication, and it contains the inverse of each of its elements. So it's a subgroup. So we need to prove it's a normal subgroup. So prove Z sub G of A is a normal subgroup. So this means we must show that if X is in the centralizer, then let's say, I don't know, pick a letter, W. W, X, W inverse is in the centralizer for all W in the group. So that means we must show that WX W inverse A is A WX W inverse. Actually, not sure this is true.
Well, the question just asks for, it's a subgroup. It doesn't ask for a normal subgroup.
Oh, that's interesting. I must have corrected that because I'm looking at an early version of this. And maybe I checked, I saw that it wasn't normal. So it's just that prove it's a subgroup. Huh. Okay. Oh, I'm sorry. Yeah, sorry. Cross this out. I was looking at problem 24, which is yeah. Yeah, I was looking at problem number 24 for that last part. So good, it's a subgroup. We're done. Glad I didn't prove it was a normal subgroup because it's not. Okay,
Can we do 18 next?
can we do 18? Let's try. 18. So we have F, let's say from G1 to G2, a homomorphism. And the kernel of F, it's all X in G1, such that F of X is the identity. And we want to prove kernel of F is a normal subgroup of G. So first of all, we know that F of E equals E, right? We prove that a homomorphism sends the identity to the identity. So the identity is in G1. If X and Y are in the kernel, so E is in the kernel of F. If X and Y are in the kernel, then F of X and F of Y equal the identity. So F of X times Y, which is F of X times F of Y, because F's a homomorphism. This is E times E, which is E. So XY is in the kernel. So the kernel is closed under multiplication. And if X is in the kernel, then F of X is the identity. And we prove that F of the inverse of an element is the inverse of F of X, which is the inverse of the identity, which is the identity. So X inverse is in the kernel. So the kernel is a subgroup. And to show that it's normal, suppose you take any element in the group and X in the kernel, what is f of Wx W inverse? That's f of W, f of X, f of W inverse. But X is in the kernel, so this is the identity. So this is f of W times f of W inverse, which is the identity. So Wx W inverse is in the kernel, which means, so the kernel is closed under this conjugation operation. No matter what element X you pick in the kernel, if you conjugate by an element W, that's in the kernel. So the kernel is a normal subgroup. That's the proof.
Professor. So we had stopped at 17 last class, so that was 18. I wouldn't mind just rolling along unless somebody has a question. So 19 would be my next.
Yeah, 1 second. All right, number 19. Let's see. So we have a homomorphism from a group G to a group G prime, and H is a subgroup of G. We want to show that the image of H is a subgroup of G prime. So what is f of H? F of H means the set of all f of X for X and H. It's like, here's G, here's G prime, here's a subgroup H, and here are the images of all the elements in H. And we want to prove this is a subgroup. So first of all, E is in H, and so f of E is in f of H, but f of E is the identity. So the identity is in this set. Suppose X prime and Y prime are in f of H. What does that mean? It means that there exist elements X and Y in H with f of X equals X prime and f of Y equals Y prime. But then X times Y is in H, because H is a subgroup, so it's closed under multiplication. And so f of x times y, which is f of x times f of y, which is x prime y prime, is an f of h, right? So if x prime and y prime are in the image of the subgroup H, then so is their product. So this product is closed under multiplication. And what about the inverses? So x prime inverse, x prime is an element in f of h, that's f of x inverse, but that's f of x inverse. And this is in f of h because x in h implies x inverse is in h. H is a subgroup, contains the inverse of all of its elements. So the inverse of an element in the image is f of something in h. So x prime inverse is in h. And we're done. That proves that the image of a subgroup is a subgroup. Any questions about that? And now we have to prove kind of a symmetric assertion. We have to prove that the inverse image of a subgroup is a subgroup. So now we have the following slightly different picture. Here's G prime. Here's a homomorphism F between them. And over in G prime, we have a subgroup H prime and F inverse of H prime. That's everything in G, which gets mapped to H prime. So H prime is a subgroup of G prime. So the identity is in H prime. So F inverse of the identity, well, actually, to make it easier. So if I take E and H, F of E is the identity in H prime. So E is in F inverse of H prime. So H prime contains the identity. And suppose we let X and Y be in F inverse of H prime. That means that F of X is in H prime and F of Y is in H prime. Those two elements get sent over here, which means because H prime is a subgroup, F of X times F of Y is in H prime. H prime is a subgroup, so it's closed under multiplication. But F of X times F of Y is F of XY. So XY gets mapped into H prime, so XY is in F inverse of H prime. So F inverse of H prime is closed under multiplication. And if X is in F inverse of H prime, that means F of X is in H prime, which means, and H prime is a subgroup, F of X inverse is in H prime, but the inverse of F of X is F of the inverse of the element X inverse. So X inverse is in H prime. So we have that if we take a subgroup H prime and look at its inverse image, first of all, it contains the identity. Second, if you take two elements in the inverse image, the product is in the inverse image. And if you take any element in the inverse image, its inverse is in the inverse image. So those are the three conditions a subset of a group has to satisfy to be a subgroup, and it's done. So that's the proof.
Somebody in the chat is asking to go over Lagrange's theorem.
Sure. So that's one of the basic theorems in group theory. So we have G, a finite group, H, a subgroup of G. G mod H is the set of left cosets of H. So this is everything in the form X times H as that goes through the set G. And Lagrange's theorem says that the order of the group is equal to the order of the subgroup times the index of H and G, where this index just means the number of left cosets. So that's Lagrange's theorem. So let's see, there are lots of ways to prove this. So here you have your group G, you have a subgroup H, you have these left cosets XH and YH. So the first thing I want to do is to show that the left cosets of H partition G divided up into sets that are pairwise disjoint. So my first claim, this is what I want to show, that X, H, and YH be left cosets if they have even one element in common, so the intersection is not the empty set, then in fact these two sets are exactly the same. And how do we prove this? So suppose that, let's say, A is an element in XH and YH. Then that means A is XH1. XH, this left coset, is all elements of the form X times an element of H for some H1 in the subgroup. And also A can be written as HX H2 for some element H2 in the subgroup. So we have A is XH1, and it's also, sorry, YH2. A is XH1 because it's in the left coset XH, and it's also Y times an element of H because it's in the left coset YH. So XH1 equals YH2 for some H1 and H2 in the subgroup. But this means that X, if I multiply on the right by H1 inverse, X is Y H2 H1 inverse. So if you take any element xh in this left subgroup, sorry, in this left coset xh, xh is, I can write x like this, y h2 h1 inverse h. And h2 h1 inverse h, these are elements of h because h is a subgroup. So this is in YH. So this element XH is in the left coset YH, which means the whole left coset XH is contained in YH, right? Just coming from this equation. On the other hand, also from this equation, if I multiply on the right by Y inverse, I can also get that, if I multiply on the right by H2 inverse, I would get that Y is equal to X H1 H2 inverse. So if I let Y little h be any element in the left coset YH, YH, I can write Y in this form, X H1 H2 inverse times H, H1 H2 inverse H is also an H. So this is an element in the left coset XH, which means every element in the left coset YH is contained in the left coset XH. And if you have two sets and each is a subset of the other, that can only happen if the two sets are equal. So if you have two left cosets that intersect, then they're equal. So in your group G, you have various left cosets, and they don't overlap. If these are the different left cosets, they have no elements in common. But if you take any element x, x is certainly x times the identity, which is in the left coset xh. So every element is in some left coset. So these left cosets partition the group. That means they divide it up into non-empty subsets that are not overlapping, have no elements in common. And G is finite. So the number of left cosets has to be finite, right? Because each of these has an element in it. You can't have infinitely many different elements in a finite set. So suppose we let G be the union of, let's say they're exactly K left cosets. That is, suppose the index of G and H, which is the number of these left cosets, is exactly equal to K. So G is the union of these K left cosets. So the number of elements in G is just the number of elements in each of these sets, and you add it all up. So the number of elements in G is the sum of these K positive numbers. But I claim the cardinality of the subgroup H is the cardinality of the left coset XH for all X and G. Because, for example, I can define a function f from H to XH and just define it by f an element H is equal to X times H. So this is 1-to-1 and onto. And that means these sets have the same size. So this is exactly K times the cardinality of H, which is H times the index. K is the index. So we just proved Lagrange's theorem. So, I mean, there's a lot that goes into the proof. I mean, there's a certain amount of group theory you have to understand, and you do have to understand something. I mean, maybe I should have stopped along the way. Are there any questions about anything that I just did? It's a lot of group theory that we did near the beginning of the term, but it's very important.
Professor, can you solve some examples from review 2?
Sure.
Thank you.
Do you have a choice, or should I just pick some?
From 1. Yeah, maybe you start with 1.
Okay.
Thank you.
This is the ring theory set of questions. So we let R1 be the set of all fractions A over B, where A and B are integers, and B is an odd integer. So a number like 8 over 5 is in R1 because the denominator is odd, and 5 over 8 is not in R1 because the denominator is even. So we want to prove, and this is when you write the fraction in lowest terms, prove R1 is a subring of Q, the rational numbers. So first of all, show R1 is an additive abelian group. So of course, 0, you can write as 0 over 1. The denominator is 1. This is an R1. So R1 certainly contains 0. If, let's say, A over B is an R1, and C over D is an R1, then B and D are odd integers. If you add A over B plus C over D, this is AD plus BC over BD. And if B and D are odd, BD is also odd. So this fraction has an odd denominator, so it's an R1. So R1 is closed under addition. And if I were to subtract, I would get AD minus BC. So R1 is closed under subtraction. So it's an abelian group. The rationals are an abelian group, and a subset that contains 0 and is closed under addition and subtraction is a subgroup. So that proves that R1 is an additive abelian group. What about multiplication? You take A over B times C over D, that's AC over BD. And again, BD is odd. So this is an R1 because the product of two odd numbers is odd. So R1 is closed under multiplication. Also 1, which is 1 over 1, is an R1 because the denominator is odd. And that's all you need to show. But you know the rational numbers are a ring, so the distributive laws hold, and that's it. We're done. So that's part. This is the first part of the problem. This is A. Prove R1's a subring. What are the units? So remember that this is the definition of a unit. X in a ring R is a unit if there exists a y in R with x times y and y times x equal 1. So we need to find the units in R1. So suppose we let x be a over b in R1. So x is different from 0 and b is odd. Well, the only inverse of x inverse, is b over a. And b over a is in R1 if and only if the denominator a is odd, which means x equal a over b is a unit if and only if both a and b are odd. So for example, if you take a equal to 5/7 in R1, the next inverse is 7/5. That's also in R1, and 5/7 times 7/5 is 1. That x equal to 6/7 in R1, x inverse is 7/6, and that's not in R1, but 6 is not odd, 6 is even. So a fraction with an even numerator is not a unit. A fraction in R1 with an odd numerator is a unit. So that's the answer to the question. Questions about that? Let me look at problem 2 then on the ring theory. It's very similar, a similar type. So here we look at a different set of fractions. R2 is all fractions of the form a over 3 to the k, where a is any integer and k is a non-negative integer. And naught means just 0, 1, 2, 3, and so forth. The integers that are greater than or equal to 0. So these are fractions whose denominator is a power of 3. So for example, 0 is a over 3, so that's an R2. So this contains 0. If I take two numbers in R2, a over 3 to the k, and y equal, let's say, b over 3 to the l, k and l don't have to be the same, x plus y is a over 3 to the k plus b over 3 to the l. I can write this as a times 3 to the l over 3 to the k plus l plus b times 3 to the k over 3 to the k plus l. So that's a times 3 to the l plus b times 3 to the k over 3 to the k plus l. This might not be reduced to lowest terms, but if I reduce it to lowest terms, I'm just going to cancel some 3's in the denominator. This is still going to be a fraction whose denominator is a power of 3.
Can you pull the paper a little bit down, Professor?
And if I subtract, it's still an R2. So R2 is an additive subgroup. And 1, I can write 1 as, for example, 3 over 3. That's an R2. And if I take this x and y and I multiply them, that's a over 3 to the k times b over 3 to the l. That's ab over 3 to the k plus l. Again, the denominator is a power of 3, so that's an R2. So again, this is the set R2 is closed under multiplication. So R2 is also a subgroup, subring. Okay. Now, let's look at number 3 then. So we have z squared brackets I. So this is all numbers of the form a plus bi. These are complex numbers where a and b are integers. For example, 2 plus 3i is an element. And 5 minus 7i is an element. If I add them, I'm just adding complex numbers. I would get 7 minus 4i. If I multiply them, I'm multiplying complex numbers. I get 10 minus 35i plus 15i minus 21i squared, which is minus 1. So 10 plus 21, this is 31 minus 20i. Right? That's just adding and multiplying complex numbers. And we define this function n from this set, it's a ring, zi to z, and you define it as follows. N, this is called the norm. The norm of this complex number, a plus bi, is just the sum of the squares of the real and imaginary points. And we want to prove that this is something like a homomorphism. We want to prove the norm of two numbers is the product of the norms. So suppose we let x equal a plus bi and y equals c plus di. And if you multiply them, you're multiplying complex numbers. This is ac minus bd plus ad plus bc times I. So you have to know complex numbers. The basic thing. So what is the norm of xy? that's going to be this squared plus this squared. So now we just do some high school algebra. This is a squared c squared minus 2abcd plus b squared d squared. That's the first term. And this is a squared d squared plus 2abcd plus b squared c squared. And you'll see that minus 2abcd and plus 2abcd, they cancel. So we're left with a squared c squared plus a squared d squared. That's a squared times c squared d squared. And b squared d squared plus b squared c squared. So that's b squared times c squared plus d squared. And I can factor out a c squared plus d squared. I get a squared plus b squared c squared plus d squared. And this is exactly the norm of x. And this is exactly the norm of y. So that proves this multiplicative property of the norm. Any questions so far? Okay. Then you want to prove x, it says a plus bi, is a unit in this ring if and only if the norm of x is 1. So what does it mean to say the norm of x is 1? If x is a plus bi, the norm of x is a squared plus b squared, and that's supposed to equal 1. Now, a and b are integers. So this a squared plus b squared is 1. This can only happen two ways. Either a squared is 1 and b squared is 0, or a squared is 0 and b squared is 1, because these are non-negative integers. The only way the sum of two non-negative integers is 1 is if one of the integers is 0 and the other is 1. And the only time a squared is 1 is if a equals plus or minus 1, and b squared equals 0 means b is 0. Or if a squared is 0, which is the same as a equal to 0, and b squared equals 1 means b is plus or minus 1. So there are only 4 possibilities. The norm of x is 1 if and only if x is equal to plus 1 minus 1. When b is 1, this number is I, and when b is minus 1, it's minus I. And each of these is a unit. 1 times 1 is 1. Minus 1 times minus 1 is 1. I times minus I, that's minus I squared, is minus minus 1 is 1. And minus I times I, it's the same thing, is equal to 1. So these are all units. So if the norm of x is 1, then x is a unit. And what about the converse? Suppose x is a unit. Then there exists an inverse y in z squared brackets I, such that x times y is 1. That's the definition of a unit. A unit is an element which has an element, an inverse, where the product is 1. So this means that the norm of x y is the norm of 1. The norm of 1 is 1, right? Norm of 1 is 1 squared plus 0 squared is 1. Norm of 1 is 1. So the norm of xy is 1, but the norm of xy is the norm of x times the norm of y. And the norm of x, remember, the norm of x is a squared plus b squared. It's a non-negative integer. So the only time a product of two non-negative integers is 1 is when both of the numbers is 1. So if x is a unit, the norm of x is 1. So that's the proof of part B. And what are the units? Well, the units are the elements with norm 1, and I already calculated them. Norm of x is 1 if and only if x is plus or minus 1 or plus or minus I. That's part 3. That's problem 3. Any questions about this? Let's see. Let's look at number 4. So suppose we take the ring Z mod 10Z. So what are the units? 1 plus 10Z times 1 plus 10Z is 1 plus 10Z, right? This is the identity. So what are the units? Well, one of them is 1 plus 10Z. 3 plus 10Z times 7 plus 10Z is 21 plus 10Z. And 21 is congruent to 1 mod 10, 1 plus 10Z. So 3 and 7 are also units. 3 plus 10Z and 7 plus 10Z. They're units. 9 plus 10Z times 9 plus 10Z is 81 plus 10Z, which is also the same coset as became congruent class is 1 plus 10Z. So 9 plus 10Z is a unit. So these certainly are units. What about 2 plus 10Z? If I multiply that by 5 plus 10Z, I get 10 plus 10Z, which is 0 plus 10Z. So this is a non-zero element and this is non-zero, but the product is 0. So if I'm interested in 0 divisors, remember 0 divisor is something, it's an element x where there's a y and xy is 0, but x isn't 0 and y isn't 0. So 2 and 5 are 0 divisors. Four plus 10Z times 5 plus 10Z is 20 plus 10Z. And again, 20 is congruent to 0 mod 10, so this is 0 plus 10Z. So 4 plus 10Z is a 0 divisor. And in the same way, 6 plus 10Z times 5 plus 10z, which is 60, which is the same as 0 mod 10. And 8 plus 10z times 5 plus 10z is 40 plus 10z. Sorry, this was 30, but same thing. 40 plus 10z is 0 plus 10z. So 8 plus 10z. So these are the zero divisors. There are only nine non-zero elements in this ring. 4 of them are units, and 5 of them, everything else that's non-zero, is a zero divisor. Remember, X is a, so this is the definition, X is a zero divisor in a ring R if X is not 0 and there exists a Y not 0 such that X times Y is 0. So you have a product of 2 non-zero elements equal to 0. Okay. Let's look at the next part of this problem. We have Z mod 11Z. Well, we don't want to make a list of units. One plus 11Z times 1 plus 11Z is 1 plus 11Z. So the identity is always a unit. 2 plus 11Z. If I multiply that by 6 plus 11Z, I get 12 plus 11Z. And 12 is congruent to 1 on 11. So 2 plus 11Z and 6 plus 11Z are units. You see 3 plus 11Z times 4 plus 11Z. That's also 12 plus 11Z, which is 1 plus 11Z. So 3 plus 11Z is a unit, and 4 plus 11Z is a unit. See, what am I missing? 5. 5 plus 11Z. I take 5 plus 11Z times 9 plus 11Z. 5 times 9 is 45. And 45 is congruent to 1 mod 11. Of course, 45 is 1 plus 44, and 44 is 11 times 4. So 5 plus 11Z is a unit, and 9 plus 11Z is a unit. So what about 7, 8, and 10? 7 plus 8Z, is that a unit? Well, 8 plus 11Z times 7 plus 11Z, 7 times 8 is 56. And 56 is congruent to 1 mod 11. So 7 and 8 are units. And if I take 10 plus 11Z and multiply it by itself, I get 100 plus 11Z. 100 is 1 more than 99, which is 9 times 11. This is 11. So in fact, every non-zero element is a unit. So the group of units is everything except 0, the congruence class of 0, which is another way of saying that Z mod 11Z is a field. Because the field is a commutative ring in which every non-zero element is a unit. So this is a basic calculation which you need to understand and be able to do. Someone asked about congruences. So if you take a positive integer m and integers a and b, you say a is congruent to b mod m if m divides a minus b. So for example, 93 is congruent to 38 mod 11. Because 93 minus 38 is, sorry, should say, yes, it's 39. 93 is congruent to 39 mod 11, because when you subtract, you get, sorry, no, this is right the first time. It's a 93 minus 38 is 55, which is 5 times 11. So 11 divides this difference, 93 minus 38. So 98 is congruent to 33 mod 11. And we take the congruence class, a plus mz. This is all integers x, such that x is congruent to a mod m. And the integers are divided up into these different congruence classes. And z mod mz is it's actually a commutative ring of congruence classes. Modulo m. But we spent several weeks learning about congruence classes, and can't squeeze it all into a couple minutes, I guess, but this is the essential fact. Look at number 10. When approved, MZ is an ideal in Z for every integer m. So what is MZ? MZ is the set of all multiples of m, positive, negative, and 0. 0 plus or minus m plus or minus 2m and so forth. So for example, 2z, it's the multiples of 2, is the set of even integers. As we call ideal, I is an ideal in the ring R if I is an additive subgroup of R and X or R times X is an ideal, is in the ideal, is in I. Let's say it's commutative to make it easier. R times X is in I for all X in I and R in the ring. So no matter what element of the ideal you pick and no matter what element of the ring you pick, if you multiply them, you stay in the ideal. For example, 2i, 2z is an ideal in Z because the even integers are a subgroup. The sum and difference of even numbers is even. If you take an even number and multiply it by any number whatsoever, it still is even. So this is an ideal. And we want to prove every ideal of the ring of integers is of the form m times z for some non-negative integer m. So take your ideal. So here's the proof. If I is just 0, 0 is an ideal. The set consisting of just 0 because you multiply 0 by any integer, you still get 0. Then I is actually all multiples of 0. So you can let m be equal to 0. So the set consisting of only the number 0 is an ideal, and it's the ideal generated just by 0. So that's sort of the simple case. Suppose I is not just 0. That means then there exists an element x in the ideal different from 0. And but then also minus x is in the ideal. Because the ideal is a group, an additive abelian group. So if an element is in the ideal, so it's just negative. If you take any integer x different from 0, either x is positive or x is negative and minus x is positive. So that means I contains positive integers. There's some positive integer in I. So let m be the smallest positive integer in this ideal I. And let n be any element of I. Divide n by m. What do you get? You get n is m times a quotient plus a remainder, and the remainder is between 0 and m minus 1. But n is in the ideal. M is the smallest element in the ideal. If m is in there, m plus m, 2m, 3m added to itself is always in there. Qm is in the ideal, which means the remainder, which is n minus qm, is also in the ideal, because this is a group. It's closed under subtraction. Now this element r is between 0 and m minus 1. So r is strictly smaller than m. But m is the smallest positive element in the group, so r cannot be positive. So r has to be 0, which means n is equal to q times m. So n, any element in this ideal, is a multiple of m. So all multiples of M are contained in the ideal because M is, and every element is a multiple of M. So I is this set of multiples of M. That's the idea of the proof. But you can't really understand this by just watching me or anyone do it. You have to look at the proof and write it down and explain to yourself, make sure you understand step by step the justification for every little bit of the proof, how you go from one statement to the next. Let's look at number 12. And remember, a commutative ring is a field if every non-zero element has an inverse. It's a unit. And we want to prove R is a field if and only if the zero ideal and the whole ring itself are the only ideals in R. Let's look at the proof going from left to right. Suppose R is a field that I be an ideal and not just zero. So that means there exists an element X in I, X different from zero, which means X is a unit. That means there exists an element Y in the ring with Y times X equal to 1, which means 1, see, an ideal means you take any elements in the ideal, X, anything you multiply by it gives you a product which is still in the ideal. So 1 is in the ideal, which means R times 1, which is R, is in the ideal for all R in the ring, which means the whole ring is contained in I, which is contained in R. So the only ideal different from zero has to be the whole ring. So this proves that if R is a field, the zero ideal and the whole ring are in fact the only ideals in R. Okay. Any questions about that? Now, how do you prove the opposite assertion? Suppose you have a ring R where the only ideals are 0 and R. So that I want to show that R is a field. So that X be in R, X different from 0, we have to show X is a unit. So if we look at x times r, this is everything in the form, let me write this as rx. This is everything in the form r times x, r in r. This is an ideal. It's all multiples of x. If you add two multiples of x, you get another multiple of x. If you multiply this by any other elements in the ring, it's another multiple of x. This is an ideal. And x, which is 1 times x, is in this ideal. So Rx is not 0, it contains x. So Rx has to be the whole ring, which means 1 is in R, so 1 equals yr times x for some r in the ring. 1 is in here, so 1 is in here, so 1 is a multiple of x, which means exactly x is a unit. Okay, any questions about that? All right, well, so maybe that's enough for this morning. We just did a lot and there's a lot to think about. I have an office hour this afternoon and an office hour, a problem session this afternoon. Another one tonight, one tomorrow afternoon, one tomorrow night, one Wednesday around 11:30. No, what time on Wednesday? I'm not sure. I have to change that Wednesday hour. I think. Let me just see what I put there. Yeah, Wednesday at 11:30. There's another office hour. So, and there'll be more, but let's stop for the morning.